Okay, so we're going to conclude the videos this week by coming up with a formula that works for general vector fields. So what we've had so far is these two coordinate-free formulas that work only for constant vector fields. But it turns out when there's a non-constant vector field that you're dealing with, you have to add some terms that make the formula a little bit more complicated. But also kind of tie into some deep, interesting concepts in differential geometry. Okay, so from now on, we're going to assume that vi and wi are functions that are not constant, or not necessarily constant. Okay, so let's recall, I'll bring this back. So recall, I mean, we computed this in two different ways, but that the derivative of alpha, d alpha, when I plug in v and w should give me this formula. So okay, and so this is what we should be getting. And if I do sort of the same procedure when I assume that v and w are not constant, what do I get? So let's try to compute. So this formula, remember, I computed it well in two ways. One of the ways was computing d alpha using my coordinate definition of d alpha. So let's try to compute sort of d alpha. So remember our first coordinate independent definition of d alpha. Oh, actually I had it right here. Is just this. So again, alpha is just a one form, and I'm computing the difference between v applied to alpha applied to w and w applied to alpha applied to v. I'm trying to assume that v and w are not constant. So what I get for the first one is going to be v applied to f dx plus g dy applied to w1 d by dx plus w2 d by dy. Okay, and then this is v applied to. Now here I have, again, f, well, let's write this as w1f plus w2g. And then now I'm going to have some extra term coming in from the fact that when v is differentiating this function, the w's can change in the direction of v. So what I'm going to end up getting is, so this is the vector field v1 d by dx plus v2 d by dy applied to w1 times f plus w2 times g. So then when I actually compute this, just taking the directional derivative as I've been doing throughout the class, I am going to get v1 d by dx of w1 times f. So this will be d w1f dx plus v1 d, well, let me just put this all in one, plus w2g dx plus v2 times d w1f plus w2g dy. So this is a term when v and w are constant, then a lot of these terms are simpler because w doesn't vary. But now what I'm going to get is dw1 times f plus dw1 dx times f plus w1 times df dx plus dw2 dx times g plus dg sorry, I'm writing the w's first, w2 dg dx plus v2 times dw1 dy times f plus w1 df dy plus dw2 dy times g plus w2 times dg dy. Okay, so now let's compare this to what I have at the top. So I have so now what I need to do is take this formula. So this is my formula for v applied to alpha of w. So now I need to also add another term. So I need to deal with this part. So when I actually add it all back together, I'm going to subtract off, basically doing the exact same thing, but switching the roles of v and w. So this will be w1 dv1 dx f plus v1 df dx plus, actually, you know what? I am on an iPad. I may as well just do this really simply. Get rid of all that. Okay, there we go. So I should be subtracting this and adding and subtracting this as well. And then now I should be changing all the V's to W's and W's to V's. So okay, so now this gives me the term that I circled in red above this W term, W applied to alpha applied to V. So now let's go through and simplify. So what I end up getting, let's cross off any terms that I see twice. So let's see, so any of the terms involving derivatives are not of W and V are not going to cancel out. But I can start looking for terms involving just derivatives of f and g. So here I see v1, w1, df dx, and I see a negative v1, w1, df dx below. Here I see v1, w2, dg dx, and I see so that I don't see below. And then I see I should see a W2 V2, yeah, dg dy, and a minus W2 V2 dg dy. Okay, now I actually have some terms that I'm okay with. So remember that I had this formula here, and this is what I'm trying to reproduce. Now using, so this is the formula I know is correct, and I'm trying to reproduce it using my non-constant vector fields. So let's see, this term, df dy, v1, w2, is right here. Let's see, w2, v1, df dy, it's right here. So that term is fine. I'm also okay with this term, negative w1, v2, df, so this will be positive w1, v2, so it'll be right here. That term is also fine. And then going through this term, dg dx, v1, w2, right here is okay. And then last but not least, this negative w1, v2, dg dx term right there is okay. So what I'm left with, so what remains is what I can write is that the difference between v alpha of w minus w alpha of v and d alpha of vw is equal to all the remaining terms. So that'll be v1 f dw1. Let's actually pull out the f's and just write v1 dw1 dx times f plus v1 dw2 dx times g plus v2 dw1 dy times f plus v2 dw2 dy times g minus w1 dv1 dx times f minus w1 dv2 dx times g minus w2 dv1 dy times f minus w2 dv2 dy times g. Okay, so this is what is left over. And I'm going to try and make sense of what this term means in terms of something that only involves the w and v and doesn't really depend on alpha. So let's try and pull out the f's and the g's. So what this ends up looking like is f times v1 dw1 dx plus v2 dw1 dy minus w1 dv1 dx minus w2 dv1 dy plus g times something. So that's v1 dw2 dx plus v2 dw2 dy minus, w1 dv2 dx minus w2 dv2 dy. Okay, and so this is the term that I am going to call alpha applied to the Lie bracket of v and w. And I'm fairly certain that I got all the signs right, but I might have a sign wrong. So we'll just keep that in mind going forward. I might have to amend some signs. So once I make this definition, what I end up getting is that d alpha of v applied to v, the pair vw, is equal to v alpha applied to w minus w alpha applied to v minus, this should be minus alpha v applied to w. Because then when I add it back over, I get this formula. So this is the coordinate-free formula for d alpha when alpha is a 1 form on R2. And I'll talk about the generalizations to when alpha is a 1 form on Rn or when alpha is a k form on Rn later. But right now, to make sense of this, the last thing we need to do is make sense of this term, which is called the Lie bracket. Well, actually, it's not. So it's called alpha applied to the Lie bracket. But we need to make sense of this term in a coordinate-free way. So we need to make sense of this without coordinates. And so what exactly are we making sense of? So if I want to call this alpha applied to some vector field, what I'm saying is that there's some vector field that whose x term is, or whose dx term is v1 dw1 dx plus v2 dw1 dy minus w1 dv1 dx minus w2 dv1 dy d by dx plus, I'm not going to write it all down again, just copy this. Plus that second part, d by dy. So what I'm claiming is that there's some vector field which in coordinates is given by this formula, and it has some coordinate-free definition. This vector field is called the Lie bracket of v and w. Lie is a person. So this defines the Lie bracket, or well, it's one way to define it. But I'm claiming there's a coordinate-free way to do it. So now let's back up and sort of try and think of a way I could combine two vector fields to get a third in a way that makes sense. Well, so let's, and in a way that when I combine two constant vector fields, I get 0. So the idea here is that, say I have some vector field, I'll just draw it, on my plane. And say I have, so let's call this vector field, it doesn't really matter which one's which, but we'll call this one V. And then I have another vector field, and I'll call it W, and it goes like this. It's always sort of tilting in a different way somewhere, where than all the V's. So if I'm at a point, say I'm at this point here, and I want to differentiate in the direction of W and then V versus V then W, do I expect to get the same thing or not? So if I differentiate in the direction of V first, then I kind of, I compute like the rise over run along a little line that goes maybe that way. And then I should be computing, differentiating in the direction of W. So maybe my W vector field goes like this. So maybe I pick a little bit of, a little distance to traverse in the W direction, sort of following the W arrows all the way. And I arrive at some point and I compute my function at this new point and sort of divide by the distance I've gone, and voila, I get a derivative. But I could have done this in the opposite order. So I could have first gone in the direction of W and then gone in the direction of V. And maybe then I don't get to the same spot. So maybe going in the direction of V first, then W doesn't get me into the same spot as W, then V. So this is the idea behind what a Lie bracket is. So a Lie bracket is something that measures this sort of mistake. And it's a little bit confusing in this dimension, but basically it's something that can't happen in one dimension. It can only happen once you have at least two dimensions. It's telling you how badly do mixed partial derivatives not commute. So you'll notice you have a worksheet problem that asks you to compute the Lie bracket of just coordinate vector fields, and you'll get that it's 0, because mixed partial derivatives, when you're differentiating with constant vector fields, are always going to commute, but they won't necessarily if your vector fields vary. Okay, so how do I take a mixed partial derivative? Maybe better to put that in quotes. Well, if I have a function, say I have a function f from, we're doing the example of R2, so let's just stay on R2. From R2 to R, then I can get a new function, which goes from R2 to R, and I'm going to call it VF, so V applied to F, because I can take a point P and send it to V at P applied to F, right? Take the directional derivative at P in the direction of F. So this is a new function. So now I can take directional derivatives in the direction W, right? So this is a new function. So now I can apply W. That can be applied to V applied to F. That makes sense. And vice versa, V applied to W makes sense. So the Lie bracket of V and W is defined to be apply V to W and then subtract applying W to V, i.e., when I apply the Lie bracket to some function, this is the function where at each point I take the directional derivative in the direction V of the function that's the directional derivative of F in the direction W, and then subtract off the same thing where I switch V and W. Oops. Okay, So this is the definition of the Lie bracket. So the final thing to do then to make sense of our coordinate-free formula for the derivative is to prove that this formula here is actually a coordinate formula for the Lie bracket. So let me get this, and we will bring it down here and make it smaller. And so the goal is to prove that these are the same thing. So that this second box, the small box, is a coordinate version of the first. Okay. So let's do this. So the way that we're going to do this is compute how it acts on functions. So if I have a function, VW applying to a function, this is equal to VW applied to a function minus WV applied to a function. So then that's just the definition. Then this is V applied to, okay, now this is going to be W1 df dx plus W2 df dy minus W applied to V1 df dx plus V2 df dy. And then now I want to take the derivatives in terms of V of the first and W of the second. So this will be V1 d dx of W1 df dy plus V1 d dx W2 df dy plus V2 d dy of W1 df dy plus V2 d dy of W2 df dy. And then similarly with the second term, so I'll just copy this, and actually I won't do that. I will actually just go through everything. So what we end up getting is minus W1 d by dx, V1 df dx. Oh, this should be a x here, sorry. And this should also be an x. Minus W1 d by dx, V2 df dy, minus W2 d by dy, V1 df dx, minus W2 d by dy, W2 df dy. Okay, so now let's rewrite this. So this will be V1 dW1 dx df dx plus V1 W1 d squared f dx squared. And then I'll get plus V1 dW2 dx df dy plus VW2. Oh, sorry, my headphones have died, so I need to plug them back in. Continued later.